Okay, so very quickly reviewing what was discussed in that previous lecture, we set up the consumer's problem, right? So the consumer's problem is to maximize utility subject to the budget constraint. And in the background, there are non-negativity constraints on the quantity choices. They can't be negative because that doesn't make any economic sense. So the lowest value for any quantity will be 0. And then we saw that at least when the solution is interior, that is, the consumer buys strictly positive amounts of every good at the optimum point, there is a very simple optimizing principle which identifies what the optimal point is for the consumer. And that principle basically says that the consumer should customize her choices so that the marginal rate of substitution between any two goods is equal to their price ratio. So MRS between good I and good J should be equal to PI divided by PJ. That's the optimizing condition. And we saw this optimizing principle through various lenses. One was mathematics using Lagrangian method. The other was diagrammatically. In the two good case, if we draw the pictures, we can see that the best point of the budget line is where an indifference curve is tangent to the budget line. Slope of the indifference curve is marginal rate of substitution, and slope of the budget line is the price ratio. So the diagrammatic analysis gives us the same condition. And intuitively speaking, what is the logic behind this condition? The MRS is the rate at which the consumer is willing to substitute good I and good J. And the price ratio is the rate at which the market allows the consumer to substitute one good for another. And unless these two are the same, there is room for the consumer to give up one of the goods and get more good of some other good in exchange, in the process becoming better off, right? So that's the intuition. Now, the thing is, this principle, MRS should be equated to price ratio. This comes with some caveats and qualifiers. In some cases, this condition in itself does not guarantee that we have identified the consumer's best choice. So read the fine print, be aware of all these caveats. So what are the caveats? Sometimes this condition MRS equals price ratio describes a minimum rather than a maximum. As you know that in the simplest kind of optimization problems, unconstrained maximization of a function of a single variable, for example, both minima and maxima are characterized by first derivative equals 0. Yes, both at the peak and the trough of a graph of a function, the tangent, if you draw the tangent there, the tangent is flat. Okay. So in the simplest case, how do we distinguish maxima from minima? We have to look at second order conditions. And in that simplest case, the second order condition says that if it's to be a maximum, the second derivative there has to be negative. If it's a minimum, the second derivative has to be positive. Okay. Now, we're not dealing with simple one variable optimization problems. We're dealing with, first of all, multivariate functions of multiple arguments, multiple variables. And moreover, we're dealing with constrained optimization problems. But there are second order conditions for these constrained optimization problems. I'll discuss them in a moment. They are sort of extensions of the idea that, at the maximum, second derivative is negative. It sort of an equivalent condition applies. An equivalent second order condition applies when we are dealing with a constrained optimization problem. So we need to check second order conditions to distinguish maximum from minimum. That's one thing. The second thing is that in some problems, it may be a local maximum, not a global maximum. Okay. A function, again, going back to the simple case of one variable function, it can have multiple peaks. Okay. So if I've identified a peak using the condition first derivative is 0, it may not be the global maximum. Yes. Trying to open up. Okay, what are examples of these qualifications that I'm giving? For example, suppose we have a utility function which is of this form. All right. If I calculate the MRS, it's marginal utility of good 1 divided by marginal utility of good 2. I'm ignoring the negative sign here. Absolute value of MRS. And that is x1 by x2. Okay. Now, I may be tempted to say, all right, this consumer will set this marginal rate of substitution equal to the price ratio. That's the optimality condition. That's one equation. I have to combine that with my budget line or budget constraint equation. That's my second equation. If I solve these two equations, I'll get the optimum values of x1, x2 for this consumer. Now, will that be the right solution?
No, sir.
No, sir.
It would be a minima.
No,
It
sir.
will be a minimum. Okay, so let me draw the picture. There's some budget line. Now, this condition identifies a point of tangency, but what do the indifference curves look like for this utility function?
Concave.
Quarter circles.
They are concentric circles with center at 0. Yes. So the tangency will basically be something like this. And you choose any other point on the budget line, let's say this, that takes you to a higher, not a lower indifference curve. So you can clearly see from the picture that this is a case where the tangency solution gives us a minimum, not a maximum. What will be the true optimum choice in this case?
Consumption of only one good.
Corner solution.
It will
It'll
be
be
corner solutions.
one of the corners, one of the two corners. If the picture looks like this, for example, if this, if the indifference curve through this corner passes above the other corner, okay, then this is the highest indifference curve you can reach on the blue budget line. If you chose the other corner, you will be on a lower indifference curve. I'm coming to corner solutions, okay? But here the tangency and the MRS equals price ratio will just give us the wrong answer. This particular case is a violation. If the utility function is like this, it violates one of the 5 axioms, right? Which one?
Axiom of convexity.
Convexity, right? So it's a violation of that. Nevertheless, if a consumer has this sort of utility function, the 5th axiom is not necessary for the existence of utility functions, right? It's the first 4 which are necessary. So we can have a consumer in principle who has a utility function like this, and in that case, you have to be careful about applying MRS equals price ratio principle. In some other cases, I will not specify a particular function, it's possible that we have a budget line and we have identified some sort of tangency point, and it is indeed a local maximum, not a minimum. But suppose the indifference curve, is shaped like this. Well, let me redraw that picture. So at a certain point, you have tangency and you have second order conditions satisfied. So you might think, oh, I've identified the true best choice. But suppose it turns around like this, okay? And then here there's another point of tangency. So we may have multiple points of tangency. And there again, this is the first caveat I was talking about. The second one. Here, the point A is a local maximum, but it's not a global maximum. The global maximum is the point B. Okay. Of course, this example that I've just drawn violates again the convexity axiom. Okay, so if we know from the start that the convexity axiom is satisfied, we will be sure that this sort of case won't arise. Neither will the first case arise. But more generally, these cases may arise. And finally, there are sometimes corner solutions. In one of the examples I just talked about, corner solutions. And when you have corner solutions, the corner solutions still have to satisfy some optimality conditions. But those optimality conditions will involve inequalities, not equalities. I'll talk more about that in a moment. In general, they're called Kuhn-Tucker conditions. So the full math of that you will learn in the math course. But often for the sake of, solving sort of two good problems, you don't have to be too formal about these corner solutions. You can often draw a picture and identify what a corner solution is. Okay, now let me talk about general second order conditions, and then I'll briefly talk about a few examples. Now, if we are dealing with differentiable functions, functions which are at least twice differentiable, then there's a nice characterization of second order conditions, which we'll take out of math books without proving it. So consider a problem of this form, a general mathematical problem, constraint optimization. We are trying to maximize some function f. X, again, is a vector, of course, many different variables, subject to gx equal to 0. So g is the constraint function, f is the objective function that we're trying to maximize. Now, using the Lagrange method, we can write down our first order conditions, solve them, and that gives us a solution. Suppose that's x star. And now we are wondering whether this is a true maximum or whether it's a minimum or some other object. So we want to test the second order conditions, right? So the mathematics of the Lagrangian method tells us from math textbooks that the second order condition is as follows, right, for differentiable functions. You construct a matrix called the bordered Hessian matrix. And this is the matrix. What is this matrix? If you ignore the first row and the first column, the matrix is basically a stacked matrix of all the second derivatives of the Lagrangian function. the Lagrangian function would be fx plus lambda, the multiplier, times gx. So you take that function, calculate all its second derivatives, and arrange them in this manner. Okay, that forms the core of your matrix. And then you add a row and a column, which consists of the first derivatives of our constraint function. Okay, so that's why it's called bordered Hessian. If we didn't have this row and column, if we just took a matrix of second derivatives, that would have been the Hessian matrix of the Lagrangian function. Okay, and we'll see the non-bordered Hessian, that the ordinary Hessian in a few slides later. But here the matrix has these rows and column, this row and this column, which acts like a border. So it's called bordered Hessian. Okay, so we construct this matrix, and then what is the second order condition? The second order condition says that the principal minors of this bordered Hessian matrix has to alternate in sign, starting with negative, right? Weakly negative. What are the principal minors? They are, you take the submatrices, okay? If you so the first principal minor is just this element, okay, 0 in this case. The second principal minor is the submatrix, the determinant of the submatrix, 0, G1, L11, and G1. You take the 2 by 2 matrix, which is part of this larger matrix, and you calculate its determinant. That's the second principal minor. Then you look at the 3 by 3 submatrix, calculate its determinant. That's the third principal minor. And our second order condition says that at the point x star, which is a candidate for the optimum choice, these principal minors have to alternate in sign. The first one is negative, second one is positive, the third one is negative, and so on. Okay, so I'm just being mechanical over here. I'm just borrowing off the shelf well-known second order conditions that you have in calculus. Now, if we apply that to the consumer's problem, okay, our bordered Hessian matrix looks like this. It's all the second derivatives of our utility function, and the borders are the prices. Okay, so this has to have to be alternating in sign. Now, you can replace the prices by the corresponding utilities. So we can replace P1 by E1. So suppose this matrix has this alternating property. Okay. Now, since the prices, remember at the first order condition, every price is equal to some constant times the corresponding marginal utility. Okay, so we can take the constant out and we can substitute this, all the prices by the corresponding first derivatives of the utility function, and that should have the same property. Now, the theory of concave and quasi-concave functions in mathematics also tells us that if a function is quasi-concave, then this matrix its principal minors will alternate in sign. So the bottom line is, if our strict convexity assumption holds up, then the second order condition is automatically satisfied. Okay, at the point of optimum where MRS equals price ratio. You can see that easily from the diagram. What this is saying is the more general mathematical argument. Take the two commodity case. This is our budget line. We have a point of tangency, and suppose preferences are strictly convex, which means all the indifference curves are strictly concave. So this part of tangency, as you can see, is guaranteed to be a maximum. Okay, if the indifference curve is strictly convex, then a case like this will never arise, right? Nor will a case like this. So that means any point of tangency is a true maximum. So that's one advantage of another advantage of our fifth axiom, convexity of preferences, that it guarantees the second order condition at the point of tangency. Okay, Ayush.
Sir, for maximum,
Yes.
determinant of the principal minor should be alternate in signs, starting with positive. Sir, but we see that the first principal minor determinant is 0. So, sir, what can we say about, means it would be maximum, minimum, or nothing?
So it, the condition is that they have to be, it consists of weak inequalities. So they have to, the first principal minor has to be non-positive, the second has to be non-negative, and so on.
Means, sir, if we get exactly 0, we would consider it as both positive and negative in weaker terms.
Okay.
Like, sir, if we get positive 0,
yeah,
then can we say it is a maximum?
Yes. So the condition is weak. Okay. So again, let's go back to the two commodity case. We don't need, for a local maximum, we don't necessarily need strict convexity. Okay, so like the extreme, you may have a case where the tangency point is like this. So if I claim this is a point of tangency, it may be that it's linear, it's straight like this. Maybe it later bends up. Okay. Now, in that case, this won't be a unique local maximum. Okay, there will be other points which are just as good, but it is one maximum. Okay, so we don't have to insist that there will be locally the indifference curve has to be strictly convex. We don't require that. And so correspondingly, in this matrix, the requirements are weak inequalities. Okay, so 0 is compatible with that.
Okay, sir.
Okay, now before I get to this,
Sir?
Yes.
So you said that the matrix should, or the principal minor should begin with negative.
Yes.
Sir, but it's written positive in the
Oh,
slide.
I'm sorry. Maybe I misspoke. Did I say negative?
But sir, I think it should be negative only.
This is
Yes, sir, given that it's starting with 0, so it should be negative.
So in the previous slide, it's written positive, sir. So which one is it? Negative or positive?
I'll clarify that. Just give me a moment. Where did I?
Yes, sir, in this slide.
Move this to the other side. Sorry, starting with positive. If you look at the second one, right, it's basically minus G1 squared. So that's always a negative number. So yeah, the first one should be positive or non-negative. The second one should be negative or non-positive. And that's the way it goes. Okay, I misspoke earlier. I'm sorry about that. All right, so just very quickly, some special cases, three examples. I'm sure you've seen these in your undergraduate days, but just for many of you, this will be a brush up, but let's go through it quickly. Suppose, first case, utility function is all of these are two good examples. Suppose utility function is x1 to the power alpha, x2 to the power 1 minus alpha. Okay. Why am I taking this case where the exponents add up to 1? That's without loss of generality. I think in your problem set, there's a question where utility function is of this form, and you're asked to show that there will be an equivalent representation of the same preferences, which is of this form. Okay, where for these to be these two utility functions to be capturing the same preferences, we need this gamma to be alpha divided by alpha plus beta. All right, so there's no loss of generality in taking this form, and this is called the Cobb-Douglas utility function. And if a consumer has this utility function, what will be the optimal choice of this consumer? Okay, now you can set up the Lagrangian, etc., etc. First of all, let's first ask the question, will the optimum choice always be interior? Okay.
Yes, sir. In this case, it should be interior.
Why?
Sir, if 1 is 0, then the whole utility becomes 0.
Oh, and you take
Sir, and IC are convex here, so it would be interior
Convexity
solution will
also.
exist.
right. I mean, it's very simple, right? If you put any of the quantities to be 0, then your utility takes 0 value, the function. But if you have any positive amounts for x1 and x2, that's a positive number, and that's strictly better than choosing 0 amount of anything. So that tells us that we will always have an interior solution for the Cobb-Douglas. So I will not bother to write down the Lagrangian. You can sort of take the longer route. I'll just skip to the condition that MRS equals the price ratio. And in this context, what will be MRS? MRS will be E1 divided by E2. Okay, and E1 is alpha times x1 to the power alpha minus 1, x2 to the power 1 minus alpha. And in the denominator, we have E2, which is 1 minus alpha, x1 to the power alpha, and x2 to the power minus alpha. Okay, and this simplifies to you can see that this x1 to the power alpha will cancel out, and similarly for x2, so we'll be left with basically x2 divided by x1, and this equals the price ratio. That's my first equation coming from the condition MRS equals price ratio. Now, there are two unknowns, x1 and x2, so I need a second equation. Fortunately, I do have the second equation, which is my equation for the budget constraint. So P1x1 plus P2x2 equals Y, the income. So that's our second equation. So we have to solve these two, and that's very easy to do. You know, you can express x2 as a function of x1. It'll be some constant times x1, and you can plug that back into the second equation and solve. All right. So if we do the solution, this is just, you know, you can easily check. The solution for x1 becomes alpha times y divided by p1. And the solution for x2 becomes 1 minus alpha times y times p2. So these are our solutions. Let me put a star to denote that these are optimal solutions. Now, these solutions, what are they? They are the demand functions for the two goods. Okay, so from the consumer's optimization problem emerges the demand functions. So this equation, the first line, tells us how much the consumer will demand of the first good as a function of her income and a function of the prices. It turns out that for this particular functioning form, the demand function is independent of P2, the price of the other good. But in general, that won't be the case. So here the cross price elasticity is 0. Okay, now, one implication of this is P1 times X1 equals alpha Y, P2 times X2 star equals 1 minus alpha Y. Okay, so what is the income elasticity of each good? You can calculate that, but
Sir, alpha and 1 minus alpha.
no.
1.
Income
So
elasticity.
1.
Income elasticity is 1, right? So that means if the consumer's income goes up by 10%, her consumption of each good will rise by exactly that same 10%. Which you can see in this equation. These two equations say that the consumer spends a constant fraction of her income on each good. Okay, an alpha fraction P1 X1 is the total spending on good one. Okay, not the quantity, but the total amount spent on good one, and that is this fixed fraction alpha of her income. And that's why income elasticity is 1. Okay? I'm not calculating it. You can just put your head down and do the calculation and find that it's 1. And it's 1 precisely because when income increases, the consumption of all the goods are scaled up in exactly that proportion. Okay. And what is the price elasticity of each good? All price elasticity?
Sir, 1.
It should be 1 only.
Also 1. Okay. So if the price of good one increases by 10%, you can see right away over here that the consumption of good one will fall by 10% because the product has to remain some constant number. Okay. If income hasn't changed, the right-hand side is a constant. So if the price goes up by 10%, consumption will fall by 10%. So price elasticity is 1. Okay. Now, let's ask the question that, is this Cobb-Douglas form of utility, is this a good canonical form for consumer preferences? Canonical form means, you can allow the alpha to vary from consumer to consumer, but you're imposing a certain structure on the preferences of all consumers. So if you want to do some empirical analysis, demand function estimation, econometrically, one way to do that would be to impose a Cobb-Douglas form and then estimate what value of alpha best fits the data, the consumer choice data, right? But if we start by imposing a Cobb-Douglas form, there are some very special features that we are building in right from the start. One of the features being this sort of income elasticity of 1. Okay, that as incomes go up, everything is scaled up. The consumption of everything is scaled up by the same proportion. Now, if we think of sort of broad patterns of consumption of most people, that doesn't sound like it's how people spend. So take food, expenditure on food, for example. Poorer households, and there's data like NSS data where you can see this. Poorer household will spend a very substantial fraction of their income, maybe 40%, 50% on the food category. Okay, whereas rich households certainly won't come anywhere close. I mean, that's going to be an amount of food they can't eat in their lifetimes. So they'll spend, much lower fraction, 5%, 10% on food. So the fraction of income spent on food varies a lot across the income spectrum. If everybody had Cobb-Douglas preferences, then that wouldn't be true. Yeah. So there's some limitations of using this as kind of functional form based on which you want to do demand function estimations from data. Now, there's one tweak to this Cobb-Douglas form that is sometimes adopted, which gives you a little more purchase, a little more flexibility in terms of trying to fit it to the data. And that's called the Stone-Geary utility function. Okay, which takes the following form. You have U equals x1 minus some constant x1 bar raised to the power alpha, and x2 minus some constant x2 bar raised to the power 1 minus alpha. So now we have three parameters, x1 bar, x2 bar, and alpha, and we can try and estimate all of these parameters from the data so that we have the best possible fit. Here, and I won't proceed much further. I think, again, there's one of the problems in your problem set where you have to derive demand functions for this more general case of the Cobb-Douglas, the Stone-Geary. And here you get a little bit of, demand income elasticities don't necessarily have to be one. You have demand functions which have kinks in them. So this allows a little bit of variation. The fraction of income spent on each good can change as income levels change, but in a very particular way. Okay, now these are the easy cases when you have nice interior solutions. The tangency condition characterizes what the optimal choice is and leads us straight to demand functions, or what we'll call Marshallian demand functions. But here, let's consider another example of a utility function. Suppose it's of this form, min of x1 by A, x2 by B. Okay, the min function, right? Everybody familiar with it. For any given x1, x2, whichever is the lower, that is what the value that the function takes. So what will be the optimum choice like in this case? Rather.
Yes, sir, I wanted to ask how the Stone-Geary function is different from Cobb-Douglas. Any special properties about this function?
In the problem set, there's you have to sort of derive the demand functions and all. So instead of spelling everything out, I'll ask you to do those derivations and then think about it, and then we can discuss it later. Yes, it is, as I said, it breaks this very special property of the Cobb-Douglas function. Right? Cobb-Douglas function, first of all, is a special case of the Stone-Geary. It's a special case where these two constants are zero. Okay. Now, in the Cobb-Douglas case, you have this very strict straitjacket that everything is always scaled up. Income rises, all the consumptions go up in the same proportion. That feature breaks down in Stone-Geary. That's not strictly true if you have positive constants sitting inside over here. So you can, in a crude way, you can generate something like what is called Engels Law. I should have mentioned that. So Engels Law is a sort of stylized empirical law which says that if I draw a picture as a function of income, the expenditure on food that looks concave. So it kind of decreases, maybe even asymptotes out, okay? Which equivalently, if I drew a picture where I took income on the horizontal axis and percentage of budget spent on food, if I graph that, that's going to be a downward sloping graph instead of a flat line. Okay, this is called Engels Law, and it's you know, I mean, if you look at the data, it's almost universally it holds in every country. So when you have the Stone-Geary form, it gives you Engels Law in a crude way, right? For the Cobb-Douglas, the graph will just look flat, as we derived, right? It'll just look flat. For the Stone-Geary, it's not quite so.
Okay, thank you, sir.
Yeah. All right, so let's get back to this min function. Now, first of all, okay, let's try to draw the indifference curves in this case. All right, what will the indifference curves look like?
L-shaped.
L-shaped curves.
The L-shaped curves. Okay. There are certain points where there's a kink. Elsewhere, the indifference curve is either vertical or horizontal. What is the equation of this? And these kinks of the various indifference curves, they lie on a ray through the origin. What is the equation of that ray through the origin?
X1
by
X1
A is equal to X2 by B.
This should be pretty obvious, right? That's where the two components of the main function are equal. That's why, starting from such a corner, if you just increase the quantity of one good, you remain on the same indifference curve. You don't go to higher utility levels. So that's why you have this. Now, in this case, from the picture, if you look at it, it's pretty obvious that the nature of the optimum point is that point of the budget line where one of these corners or kinks appear, right? You choose any other point which is not on a corner or kink, that's not optimal. So if you chose this as a consumer, you can always move here and that'll take you to a higher indifference curve. So how do we mathematically then write down the demand functions? What are the equations?
Here we will equate x1 a upon is equals to x2.
Right. From the picture, we can see that, you know, it'll be one of these corners. So that means the equation x1 a divided by a equals x2 divided by b. This has to be true. So that's our first equation. And then p1 x1 plus p2 x2 equals y. That will be our second equation. And now we solve, and that gives us the demand functions for x1 and x2. The reason we can't use the MRS equals price ratio principle is what?
Because it's
non-differentiable.
Non-differentiable, right? So there's no unique slope at the point of the kink. However, broadly speaking, it's the same principle. It's almost like a tangency, yes, except that we have to get around the fact that it's not differentiable over there. This is the case, as you know. This is called perfect
Complements.
Classic example is left shoes and right shoes. Okay. If for some reason shoe companies sold them separately, we would still not, you know, having two left shoes and one right shoe is as good as having just one pair. Okay, that second left shoe is of no use to me because there's no right shoe to go with it. So that's the kind of thing that this is capturing, perfect complements. A third popular example is a utility function, which is u equals, let's say, ax1 plus bx2. Okay. So if I draw a picture, what will the indifference curves look like?
Straight line.
Straight lines.
Straight lines. Slope?
A by B. Minus A by B.
A by B. Okay. Here, if you were kind of asleep at the wheel, I gave you this utility function and you say, okay, I know MRS will be equal to price ratio. What is MRS over here?
A by B.
A by B.
A by B, set that equal to P1 by P2. And we get a rude awakening. This is useless because everything here is our parameters. X1 and X2 don't figure here. So this is of no use to me to solve for the optimal values. Now, if I start looking around and trying to understand what is happening, why am I not getting? That's because you have to draw a picture. This is the budget line, the blue line. One possible scenario is where these indifference curves are steeper than the budget line. Okay. Then obviously the optimal solution will be a corner solution. You pick this point, you can move to this point, and that will take you to a higher indifference curve. And you can move to this, which will take you to an even higher indifference curve. And so in this case, the way I've drawn it, the best choice is this corner. Okay. On the other hand, if I'll just use a different color on the same picture, suppose the indifference curves were flatter, shaped like this, okay, then whatever point you pick in the interior, if you move up and left, you move to higher indifference curves. So you keep going till you hit the other corner. Okay. So in the case of the red shapes, the optimal choice is this corner A. In the case of the green shaped indifference curves, the optimal choice is the other corner B. Okay. Now, when do we get A? When do we get B? Well, as is clear from the picture, it depends on the relative slopes of the indifference curves and the budget line. We'll have this corner solution when if I'll first write the condition and then I'll write the values. Well, okay. A, so x1, x2 at A, what are the values of x1, x2? X1 is obviously 0. And all the money is spent on the other good. So the amount is y divided by P2. Okay. These are the demands when the true solution is A. And when do we get this? When?
MRS is less than price ratio.
When the indifference
A by
curve
B
is
is
flatter.
less than PX by P, P1
Yes.
by P2.
So the indifference curves are flatter than the budget line means the slope of the indifference curves, namely A by B, is greater than slope of the budget line, which is P1 by P2. Now,
Sir, shouldn't A by B less than P1 by P2?
Since we ignored the negative signs,
sorry, yeah. Well, less than P1 by P2. And the other corner solution obtains when we have the opposite inequality. And you have a very special case where things are indeterminate. I mean, there are multiple optima. This is where x1 belongs to, could be anything from 0 to all the income being spent on x1. This is the case where the two slopes are identical. Okay. In that case, the budget line itself is an indifference curve. Okay, so any point of the budget line gives as much utility as any other point on the budget line. So there are multiple optimum choices. Anyway, so this is the kind of way to write down the demand functions when you have these corner solutions. And what you have to check for a corner solution is inequalities like this. Okay, these are the general version of this is what is called Kuhn-Tucker conditions. But in simple problems, you can just do it diagrammatically using common sense and intuition by drawing the picture and saying, okay, the condition I need is the indifference curve is flatter. That means this. And so using those conditions, you can write down demand functions in cases like this. And then you can have all kinds of hybrid cases. So let me just briefly mention a fourth example. So suppose the utility function is let's say max okay, A is some constant. I'll take it to be, I think I'll specify it later. A is some positive constant. Okay, what do you think the indifference curves look like in this case?
These are perfect.
So straight lines, Thomas open.
Perfect substitute.
It depends on A.
It'll actually be perfect substitutes.
Yes,
They're perfect substitute.
First of all, so okay, first order of business, I want to draw pictures of the indifference curves, capturing their shapes. Before that, I may want to, all right, so
It will be like V, and there will be a 45-degree line.
so draw a picture. Let me draw the 45-degree line as someone just suggested. So the, which is min, which is max, depends on whether we are above the 45-degree line or below the 45-degree line. Okay, so let's take each region by turn. So above the 45-degree line, so I'll break down the utility function into a piecewise linear form. I mean, it is piecewise linear. So I'll write what the utility is if we are above the 45-degree line. Above the 45-degree line means x1 is less than equal to x2. Yes. And we'll write what the utility function looks, what is expression if we are below the 45-degree line, which means x1 greater than x2. Okay. So tell me what the first piece ought to be. If we are here, then the first component becomes, it's the max.
AX2 plus X1.
AX2 plus X1. And by the same token, the second component or piece is AX1 plus X2. Okay. So what
Excuse me, sir.
Yes.
So don't we have to think of the sign of the A?
It's some
Because
positive
if it is
number.
negative,
It's some positive number. Yes,
okay.
A is positive. Okay, so above the 45-degree line, an indifference curve will be a straight line. Yes.
Sir,
Yes.
but when A is from 0 to 1, the indifference curves will look different from what
I understand. I'm coming to that. I'm going step by step, right? What you are getting at will emerge in just less than a minute. So above the 45-degree line, this is the relevant expression. Okay, so that's the equation of a straight line. If I set this equal to a constant, that's the equation of a straight line. So the indifference curve above the 45-degree line is a straight line. What's its slope?
1 by
1 by
A.
A.
1 by A.
Minus 1 by A. And below the 45-degree line, it's a straight line, but a different straight line. And what is the slope?
A.
Minus A.
Slope is minus A. Okay. Now, if A is less than 1, suppose I've taken A to be between 0 and 1, then the slope above the 45 is steeper above the 45-degree line and flatter below. Okay, then this is the shape. In the case where A is greater than 1, our indifference curves will look like this. Okay. Now let's focus on this case. At least the indifference curves are convex, right? They're weakly convex. They're not strictly convex because there are portions where it's linear. So it's weakly convex, but at least it satisfies axiom 5 weakly. So over here, what will the best choice be for the consumer? Well,
It will depend on the budget line.
yes.
Yes, sir. It
So
depends on
sometimes it'll be the kink. Sometimes it'll be a corner solution. All right. So I won't solve it out wholly. Again, I think this appears in the problem set, if I'm not mistaken. So I'll let you work out everything, write down the demand conditions. The demand functions will themselves have to be written in multiple lines like this with conditions attached, that if this is less than that, then these are the demand functions. If that is more than this, then these are the demand functions, etc., etc. But in all of the, here again, you see that, we can't launch into marginal rate of substitution equals price ratio because, first of all, in a lot of the cases, we'll have corner solutions. And in other cases, we'll have a solution at the kink where the function is not differentiable. So you can't just run on autopilot and identify the maximum using MRS equals price ratio principle. Okay, but in all of these cases, which are favorites for exam problems, you get a handle on it. I think if you are if you look at the utility function carefully and draw the indifference curve map and get an idea about what shape it takes, and that will tell you when you have corner solutions, etc. All right. Okay. Okay, I have about 10 minutes, so I want to get through 2 more important results. Not sure what's happening here. Okay, you guys can see my screen, right? Yeah. All right. So I want to talk about two important mathematical results, which are going to be very useful and are used repeatedly in this sort of classical micro theory. They're called the implicit function theorem and the envelope theorem. So I want you to understand the math as well as the intuition. Okay, so let's focus on a constraint optimization problem of a general kind, right? Abstract, not any particular economic problem. So we're trying to maximize some function f. It's a function of a vector of choice variables, endogenous variables, which is the x vector, and a vector of parameters, that's the a vector. Okay, so each of these are vectors, they're in bold. So these parameters or exogenous variables are given from outside, so we are not allowed to choose them. And there's a constraint, and the constraint can be written in form of equations or in form of sets. So here we have written it in the form of a set, that x has to be chosen from a restricted domain. In the consumer's choice, for example, it had to be chosen from the budget set, right? All the points on the budget line or below it, those are the ones that she can choose from. The ones outside are infeasible. So in a more general problem, we have this kind of objective function, which is being maximized subject to some feasible set, you may call it. The x's have to come from the feasible set. Now, suppose we have solved this problem. Okay, we've solved this problem for every possible vector of parameters or exogenous variable. So you give me one set of parameters, I solve the problem, find the optimum x. You give me another set of parameters, again I solve the problem, find an optimum x. Right, so I walk through the day, I work out the optimum value of x for every vector of parameters a, and that gives me this function x star as a function of a. In the consumer's case, the consumer's optimization gave us the demand functions as functions of parameters of the consumer's problem, namely income, prices, etc. So this is called the choice function. Okay, for a general constraint optimization problem, once we have solved it, that solution is captured in the choice function. Okay, what values of the endogenous variables give us, solve this problem for us for every possible vector of exogenous variables or parameters. Now, the other object to define is the value function. Okay, and the value function is just the maximized value of this function subject to the constraint. Another way to define the value function is to say that, well, if I plug in the choice function into my objective function, okay, if I plug in the optimum x, right, the x which solves this problem into my objective function, then the resultant function is called the value function. Both the choice and the value functions, you will note, is a function only of the a vector. Okay, the value function is also a function of the a vector because we have already solved for optimal x choices and have incorporated it in our calculation. So at the end, in the end, we get a value which is a function of all the parameters of the problem. Now, okay, so now let me put that aside. Let me get to another thing. I'll come back and use these definitions when I'm talking about the envelope theorem, yes, which I'll get to in a moment. Now, let me talk about the implicit function theorem. In many economic models, the model essentially boils down to a system of equations. So if you take the model of consumer's optimization, rational choice of a consumer with well-defined preferences, what did we do? We set up this constraint maximization problem, utility maximization given a budget constraint, and we apply the first order condition. And as long as we have an interior solution, we got a system of equations from those first order conditions. When we solve that system of equations, it gives us our demand functions, right? So the consumer choice model boils down to the first order conditions, the system of equations defined by the first order conditions of the problem. Take the market model, right? Let's jump a level higher and there's n commodities in, there's a vector of prices, and in the market for each good, there has to be, in equilibrium, there has to be market clearance, right? Demand and supply have to be equal. That's the heart of classical price theory. So there again, the model boils down to a system of equations, isn't it? In each market, demand equals supply. So we have, if there are n markets, n goods, we have n market clearance conditions. That defines the model. So in abstract general terms, we can think of an economic model as a system of equations, therefore. All right. And often the question we ask of a model like that is, what happens when some exogenous variable or parameter changes? So in the model for consumer choice, we are interested in questions like, what happens if a good becomes more expensive, if petrol becomes more expensive? What happens to the demand for petrol? What happens to the demand for cars? What happens to the demand for, clothing and so on? Okay. So we are constantly starting from a system of equations and then doing some comparative statics exercise, meaning we are shifting some parameter and then asking how do the endogenous variables shift in response to that. Now,
Sir,
yes,
so isn't that comparative statics only?
that's what I just said.
Okay, sir.
We start with a system of equations and try to do comparative statics on it. Okay.
Okay, sir. Okay, sir.
Now, that's where the implicit function theorem comes in very handy. Okay. So consider a system of n equations, and we'll take them to be differentiable so that we can apply calculus. We have n endogenous variables, that's the x vector, and m parameters, that's the a vector. Okay. And our ith equation in our system, so we'll have n equations because we have n unknowns, and the ith equation is of this form. Some function fi takes the value 0. Okay, we'll write these always in the form that on the right hand side we have 0. One question is, when does a solution exist? And the second question is, how can we do comparative statics? Okay. Now, it's very easy to do comparative statics when you start with particular functional forms. If I tell you that the consumer has Cobb-Douglas utility function or Leontief utility function, like that min function, or any other utility, or Stone-Geary, CES or whatever, then doing comparative statics is easy because you can have closed form solutions for your demand functions, right? You can actually write down a function which is the demand function. But often we don't want to assume that. Okay, so for many general questions, we don't want to say, oh, consumers have Cobb-Douglas preferences or this preference or that preferences. We want to work with general functions, general U functions, which have some minimal properties like it's quasi-concave, so that we have convexity of preferences. We don't want to assume anything more than that. But even without specifying the functional form, we want to make statements like, if price of something goes up, its demand will go down, right? Would love to make sort of statements like that or derive theorems like that, even without specifying the functional forms. Now, how do we do that? right? How can we, if we can't explicitly solve for our system of equations because we don't know what the functional forms are, we only know some general properties, then how do we do comparative statics? And that's where the implicit function theorem is so useful. Okay, now this is our system of equations. We can construct what is called a Jacobian matrix. What is the Jacobian matrix? For each function, there are n partial derivatives, first partial derivatives. So, in my Jacobian matrix, the first row will be all the first partial derivatives of our first function in our system of equations. The second row will be the first partial derivatives of the second function. And the last row will be all the first partials of the nth function. So you stack them up like this, and this is called the Jacobian matrix. And if the determinant of the Jacobian matrix is non-zero everywhere, then an explicit solution exists. But more importantly, the Jacobian matrix can be exploited to do comparative statics analysis. So let me talk about that. So this slide is a bit difficult to decipher. The notation is a bit cryptic, but let me explain both what this means and why it's true. So we have our first equation, f1 x is the vector, a is the vector of parameters, that's equal to 0. Okay. F2 x equals 0 all the way down to fm. Now, in principle, I can solve all of this, and I can find, x1 as a function of a, x2 as a function of a, and so on. This is my solution, if it exists. Right? The vector, solution vector, let's call that x as a function of a. Now, if I substitute inside each of these functions, not some arbitrary x, but this solution itself, then by definition, these equations become identities, right? Because xa is defined to be that x vector which satisfies all of these equations. So by definition, each of these things have to be true. So and so on down to fn. Okay, and now suppose I suddenly get interested in let's say the kth parameter. So suddenly I start asking questions, what if this AK parameter, which could be, for example, the kth price in the consumer's problem, what if this goes up, right? How does this entire solution move if this kth parameter changes? Okay. Well, what we are asking is then essentially, what is the nature of this, d x1 or xi dak? The k parameter shifts, what happens to the ith endogenous variable obtained from this set of equations? Well, let's go back to these identities. They're the ones that define our solution. And because it's identities, we can differentiate, we can take derivatives of the two sides with respect to something, and those derivatives have to be equal. So let's differentiating each side with respect to the parameter that we are interested in, namely ak. So derivatives with respect to ak. Okay. So what happens if I differentiate the left-hand side here? I'll have a bunch of terms. I'll have, first of all, del F1 del x1 times dx1 dak, right? The kth parameter change will affect the value of x1, and that change in x1 will in turn affect the value of this function f1, right? So that's captured in this first term. Then we'll have a second term, which is the same function, partial derivative with respect to x2 times how much x2 changes in response to shift in the kth parameter, and so on till del fn del xn dxn dak. All right. Now, there's one additional term which I have missed, which is what? AK is itself an argument of this function, right? So when AK changes, it directly affects the value of the function. By how much? By the amount del F1 del AK, right? So this last term added equals 0. So if I take this last term to the other side, I'll get a minus this. Everyone with me? I'll wrap up shortly, right? Just give me just a few more minutes. So I can do the same. I can now move down to the second function or the second identity, and I can start differentiating both sides with respect to AK. And I'll have exactly the same kind of equation, except that I'll have to substitute the superscript 1 by the superscript 2. So, you know. And so on. And when I come to the final thing, I'll have a del F2 del AK, and so on. Now, if you look at it closely, you'll find that this system of equations involving derivatives, this can be summarized in a neat way, which is a matrix times a vector equals another vector. I can write it in this form. What is this vector? This is the vector of all these. Remember, in every line, the first thing, in the first place, we have dx1 dak. The second place, we have dx2 dak. And so the vector over here is dx1 dak, dx2 dak, going all the way down to dxn dak. And what is the matrix? Again, if you just look at these equations closely, the matrix is basically, the first is del f1 del x1, del f1 del x2. Okay, those are the coefficients appearing on the first line. So del f1 del xn, sorry, and I'll just write the last line, del fn del x1, going all the way to del fn del xn. And what is the vector on the right hand side? It's all these things that we got on the right hand side of these equations, right? Of these equations. So we have minus del f1 del ak, minus del f2 del ak, down to minus del fn del ak. Now, if you look at this, this is something that we just defined a moment ago. This is the Jacobian matrix. Okay, that times the vector of comparative static terms. This is what we are interested in. If the parameter k shifts, what happens to all these endogenous variables? Which way do they move, at what rate? So this is our vector of interest. And this is a vector of these partial derivatives. Now, this is linear algebra. And again, I'll borrow stuff off the shelf. If we have a system of linear equations like this, we know how to solve them in linear algebra. We have to apply what is called Cramer's rule. And Cramer's rule tells us that the solution for the ith element over here, okay, the ith element would be dxi dak. That takes a very simple form. Again, I'm not proving it. I'm borrowing Cramer's rule from our linear algebra textbook, which says the solution, the ith solution over here, is given by a ratio of two determinants. In the denominator, you put the determinant of the Jacobian matrix, you calculate that, put that number over here. In the numerator, you calculate the determinant of a different matrix, which is, let's call it Ji. I think in the notes, I mislabeled it. I put K here. I should have put I. I'll make that correction. So what is this thing? This thing is basically, you look at the ith column of the Jacobian matrix. You replace the ith column by this vector. So you can construct a new matrix, which is almost the Jacobian matrix, except that its ith column has been replaced by the vector on the right-hand side. And then you calculate its determinant. So Cramer's rule, fortunately, from linear algebra textbooks, tell us that this is the way to solve a system of linear equations like this. And so this is the way to do comparative statics. Okay, we can say something about how things will move around, at least maybe qualitative things, that this will go up, that will go down, without necessarily knowing the form exactly of these functions. Okay, using this solution, right? So this is the engine of doing comparative static analysis. You start with the system of equations that defines the model. You do this sort of analysis that gives you expressions for comparative statics, namely these derivatives. And sometimes you can assign signs or say something about the nature of these derivatives from these expressions. In your problem set, I have tried to sort of drive this home even further. For example, I've given you a problem on cricket, how to adjust a cricket team when your opponent's bowling strength goes up. And using these same methods, you can say something a little bit intelligent about that question using methods like this, right? So take a look at that problem to further understand how comparative statics is done. And obviously then, the denominator has to be non-zero, right, for this exercise to make sense. So now you can relate it to the condition that the Jacobian matrix has to have a non-zero determinant for a solution to exist and for us to be able to do comparative statics. Okay, so I am going to stop there because I'm out of time. So in tomorrow's lecture, I'll start with discussing the envelope theorem. Yeah. So I'll stop here now and take questions if there are any.